Okay, let's get going. I want to start off by talking about the homework. Go through that. Okay, so first question was about the wages model and using data from the American Community Survey. Anyway, this is administered by the same people who do the census, so it is fairly high quality data. The census is like the only organization that can put you in jail if you don't comply with the thing, and so they get you know, this wages data or whatever, they get authorization to view that information from your tax returns and stuff like that. So it's about as good as you can get, and you can get it for all 50 states, and you can get it for a large number of years. The one we were using is actually from Oregon, which is a weird state, but you know, a lot of the people live in like Portland, and that is a relatively affluent place, but there's also, at least by area, a lot of stuff to the east part, which is very rural and pretty poor. Anyway, so we're talking about a generative model for wages. You want to approach it from a Bayesian perspective, but even if for whatever reason you weren't using a Bayesian estimator, it's important that you know, or be somewhat familiar with, could do a basic version of all the basic models in political science or economics or sociology or psychology to be have a good background in applying quantitative methods to social science problems. And this one for microeconomics, labor economics, is really one of the most basic ones that you could and should be familiar with. And people were asking on campus why, like, what do I put in these things? There's hundreds of papers about modeling something related to wages that you can just pick, any one of them and go from there. So a particularly easy and common model for actually log wages is been done for years, but originally by somebody named Jacob Metzer. It has a Wikipedia page, but basically it says that log wage is a function of years of schooling along with quadratic relationship based on years of potential experience. And usually the trick is to get some measure of years of potential experience. So you could start with a model like that, or one similar to something like that, and then once you get that going, you can start adding other things like the race and particularly the gender. These models were historically developed to apply to men, particularly men who work full time, and they're known to not work at all for women, really. And so at a minimum, you would probably want to let all the parameters vary between men and women. But you can start with a model that is too simple, and then you can use things like leave one out cross-validation to say, well, this, adding more complexity to a model like this is worthwhile or not, depending on whether it's expected to predict future data better. But when you do that, and it's really a fine way to start from a simpler model and then building up to a more complicated model. But when you do that, you want to plan out the models and the priors and whatnot in advance, not letting the posterior distribution of one model affect your priors for a more complicated model if you're going to be estimating them all on the same data. Of course, in this case, you can go back and get data from like the 1990s or something like that. And if you needed to play around with it, that's fine. And then, do the more recent 2017 model. There's nothing wrong with any of those. So we're just going to do one model here, and we'll do it for log wages. A number of people tried to model wages directly, which is perhaps possible, but you would want to take, it's not something that's very commonly done in labor economics. It's almost always log wages whose errors are reasonably normal. But if you were going to do something with just wages, you would want to choose some sort of specification to ensure your model wasn't predicting negative values, which can sometimes be the case, but obviously doesn't make any sense. These particular data, although they're kind of the best ones we have, don't really have any great measures of years of potential experience, like training in a particular sector or anything like that. So we'll just have to make do with age. And then so in a generative model, we have endogenous known. In this case, it's going to be log wages. And so if log wages is the endogenous known, then wages would be an endogenous unknown that you can get the distribution of if you had some model for log wages. The exogenous unknowns in a linear model, the intercept, the coefficients, and sigma, the standard deviation of the errors. Exogenous knowns, the number of observations, the number of predictors, etc. In this case, predictors are educational attainment and age plus squared age. And then also in exogenous knowns, you're putting the prior means and prior standard deviations. If you're going to use normal priors, which would have been fine for the next problem on the intercept and the coefficients, well, what are the means and the standard deviations of those normal priors, in addition to prior rates on the, let's say, exponential prior on sigma, the standard deviation of the errors. And so these things that complete the specification of your priors also part of exogenous knowns. You don't have to know what the parameters are, but you do have to know what you believe about the parameters, and you have to be able to express that in terms of concrete probability distributions. And then the endogenous known wages, or in particular, we're going to do a couple problems, the average wage across people in Oregon without having the subject of top coding the high incomes. Questions about that? Okay, so what would be a reasonable prior R squared? Hard to go too low, just because these predictors are not exactly ideal ones. But I put in a prior median of about 0.2, and then you can go on to draw from the prior predictive distribution. So I'm gonna, to make it a little bit easier to specify priors, I'm gonna change ages from years to decades. And center it. That makes it a little bit easier to specify the coefficient on the interaction term, but Stan is going to center the predictors. Anyway, it's just a question of whether you see the output in centered or uncentered form. So I changed the decades and center it, and then you could just put in like a fake outcome variable and then put in the predictors and specify what priors you want. So this is going to be on log wages. So I sort of guessed at what the average wage for somebody would be in log units, taking into account that the top coded values are lower than they should be, but it had sort of a relatively large amount of uncertainty as to what the prior intercept would be. And then for the coefficients, respectively, on schooling, the linear term on age, the quadratic term on age, put in small prior means, but certainly positive for schooling and age, and negative for age squared, so that the functional form is going to be like this as opposed to like this. So the squared term on age should probably pretty definitely be negative, and the linear term positive. Those you can be relatively precise about. They're not going to have huge effects. And then, some prior exponential prior on the standard deviations. Again, that is going to be in terms of the rate, which is the reciprocal of the expectation. So, you know, those are also going to be pertaining to log units. So I used about a rate of 40, which may have been a bit too big. Anyway, prior PD is true. You don't need a whole lot of draws to make the assessments that are asked for in this, which is to calculate the from the ratio of the variance across people, the ratio of the variance of the linear predictor, which in the case of a Gaussian model, or identity leak function is going to be the conditional mean divided by the variance across people of the posterior predictions, which includes the contribution from the error term. And so in principle, the denominator should be bigger than the numerator. And so this conceptually aligns with the definition of R squared that you've probably heard before. It's just in this case, we get a distribution of it. And in this case, we can get its distribution before we actually deal with the wages data. We can get the distribution of the R squared implied by our priors on these coefficients that pertain to these variables. And, you know, with a little bit of trial and error, you can probably get that to come out pretty close to what you said for the prior median in problem, you know, 1.2, but it involves sort of making the error variance or standard deviation a little bit bigger, a little bit smaller relative to the coefficients in order to get something, you know, in the right ballpark, or not right, but consistent with what you said before. So a lot of Bayesian statistics is just about eliminating contradictions in your thought. So if you think that there's like a huge effect of schooling, you're going to be disappointed. But if you think there's this huge effect of schooling and the R squared is like 0.07, then those two beliefs that you have are pretty much impossible to reconcile with each other. And so maybe think a little bit harder about, do you really believe the coefficient on schooling is that big if you think the, you know, proportion of explainable variation in log wages is that small, etc. Anyway, just bring your prior beliefs into balance, and then, you know, you're pretty much ready to go. But you should also make sure that the implied prior distribution of wages rather than log wages makes sense. So you just need the EXP, the posterior predicted distribution of log wages, and then you can do various things, histograms. Here's an empirical CDF. So, you know, most people are not making, you know, all that much money, and I cut it off before it got to like, you know, millions and millions of dollars. But, you know, not so many people are making over like 100,000. So this might be somewhat reasonable for a distribution of wages. Questions about what I did with that? Yeah?
How can you use the rate for the residual variance?
Right, so that's an exponential prior, or it could have been some different things, but I use an exponential prior. And so then you sort of think about your expectation for that, and then just take the reciprocal of it. But honestly, I just sort of kept playing around with it until I got the R squared that I thought would be.
But the residual variance was assumed to be normally distributed in these models.
The errors are normally distributed. We don't know sigma, the standard deviation of the errors, but we have a prior about it, which is going to be a strictly positive and often skewed. Other questions? Mark?
The prior is the distribution for the coefficients. And so if you put normal, are we saying all the coefficients are distributed?
Yes. So they can have different means and they can have different scales. But RStan ARM does not allow you to mix like a normal prior with some other family. When you're writing your own STAN programs, or even when you're doing BRMS, which we'll do after spring break, then you can. So there's no rule that says like, if one prior is normal, all the priors have to be normal. It's just our STAN arm is intended to be relatively simple. So there's a number of prior choices, but not like infinite prior choices, in part because like these STAN programs have to be written and compiled. So you can't just like support everything. Other questions? Okay, so then we go to condition on the data. We call STAN LM. R2 equals 0.2, what equal median, to say that this is our prior median about R squared. By default, it's the mode, which would be fine as well, but that's not what the question asks for. So you may have to bump up adapt delta to reduce or eliminate the number of divergent transitions, but even still, some of you found that you couldn't completely make those go away, in which case you should probably revisit your specification of the model, but Stan is telling you there's something about this posterior distribution that it's extremely hard to sample from in some region of the parameter space. And we'll talk more about diagnosing those things. But anyway, just sort of taking the output at face value, we get a posterior R squared, in this case, of 0.29. So that would be higher than my prior median. But others of you, put in like 0.5 for the prior median and got, 0.1 for the posterior median, in which case for you it would be low. But anyway, you update your beliefs about all the parameters inclusive of the R squared. And some people were like pretty surprised by things, but that's, what happens when you update your beliefs a lot. Questions? No? Okay, then, so the sample, or in the data, there's top coding, which is a very common thing with surveys about income. So they get your signature to like, well, you have to give them your signature, but they force you to give you your signature for them to pull your tax returns from the IRS, and so they look at your wages. But if you were in Oregon and you earned more than 393,000, they just put it as 393,000 in the data, and so cutting off the wages at the very, very top end, some doctors and lawyers and certainly in New York, financial managers and things like that, although such people would often have income that's not classified as wages. But anyway, your posterior predictive distribution is not going to be subject to that top coding, and so it's probably a bit better measure of the average wage than what's in the data, because what's in the data is known to be biased downward due to the top coding of extremely high incomes. Our STAN or STAN LM doesn't exactly handle this right. You would also want to tell STAN that the omega for the outcome, the sample space of the outcome, is just like 0 to 393,000 or the log of 393,000. It's actually sort of using all real numbers. So it would be better to incorporate this knowledge that we know about top coding into the likelihood. And STAN LM doesn't do this, but you could do it yourself if you were writing your own STAN programs. But anyway, looking at the posterior predictive distribution of wages and what is its average across people is probably a better measure of what the average wage is than the average wage in the data when it's subject to top coding. And indeed, we see that in the histogram of the distribution of wages. So anti-log, the posterior predicted distribution of log wages, put it back into dollars, and we see, our beliefs about what is the average wage in Oregon are, reasonably well concentrated between 55,000 and 60,000 for its, posterior distribution, but the average in the data was only like 48,000, something like that. And so that's actually an entirely plausible difference because these very large incomes have a large effect on means and variances and things like that. Not so much about medians, but things that are expectations. They can have a big effect on it when you have a distribution that's very skewed, such as wages, but even more so wealth. Stuff like this can happen. John, question? No? Someone? So you may very well have gotten something like this. Okay, bivariate Poisson. It's another thing like many on Wikipedia that's not super well known, but it's a good exercise for coding this sort of thing in Stan. Even though we didn't exactly use it in the third problem, we did something similar, but it's good to get practice coding these sort of 20-line pieces of Stan programs and building up your ability to do that, because once we get into April, we're going to be starting to put these like 20-line pieces of Stan syntax together to build your own Stan programs. And at that point, you'd be in a position to model some bivariate count outcomes, such as the number of Twitter followers and the number of accounts that a Twitter account is following, which we would expect to be positively correlated. So in terms of drawing from the prior predictive distribution, first you're going to need a function to draw from two counts that are positively correlated. And I gave you this much, but basically you're just drawing 3 Poisson random variables that you don't actually observe. What you observe is x1 and x2, x1 being the sum of the first and the third, and x2 being the sum of the second and the third. And the presence of this y3, which is going to be a positive count, induces this positive correlation between x1 and x2 that we often see in counts. In terms of drawing from the prior predictive distribution of a model like this, so first we're going to be, for each of our simulations that we're going to do, from the prior, draw lambda 1, lambda 2, lambda 3 from their respective exponential prior distributions, given the rate values that you pass in for each of those, and then given the realization of lambda 1, lambda 2, lambda 3, then calling the Poisson RNG function to get back an integer array of size 2. For Stan is a bit more strict than R, and so you can't, strictly speaking, put an integer array into a row of a matrix, because the matrix is implicitly containing real numbers, but you could just do it one scalar at a time, or you could use the 2-row vector function to convert it from an integer array of size 2 to a row vector of size 2, and then you can slide it in to a matrix that has 2 columns. However you want to do that. It's all fine, and then you return it at the end. A lot of people had more trouble with this than I had hoped, but really you can just see this as just the same as like bowling. When we did that the very first week, there's some probability distribution for what happens on the first roll, and then given what happens on the first roll, there's some conditional probability distribution that happens on the second roll, and we can draw from each of those 2 distributions. And so lambda 1, lambda 2, lambda 3, that's like the first roll in a frame of bowling. That comes first, and then conditional on the realizations of the first roll. Then what comes second is drawing from the distribution of the data, which in this case is 2 unbounded counts. But so now what's first is the prior, and what's second is the data before you see it, but it's still this 1, 2. Draw from the marginal distribution of the parameters, draw from the conditional distribution of the data given the realization of the parameters, just like we did, second day or whatever, draw from the distribution of the first roll of a frame of bowling, condition on that, draw from the second roll in the same frame of bowling, and you can look at the margin of whatever is second, in this case, second being the data, And that marginal distribution of the data for the bivariate distribution between parameters and data is what we call the prior predictive distribution. It's what you believe the data to look like before you collect it, taking into account the fact you're uncertain, probably highly uncertain, about the parameters generating the data under your model in a generative process. And so, you know, it's just like that, or it's just like poker when you have some, you know, distribution about what the other person's hand is, and then they bet all of their chips, and now you're updating that, and now you have a conditional distribution for, you know, what pertains to it. And so that's a lot of these things that we sort of used in a very stylistic, abstract, or stylistic way the first few weeks of the course really have direct analogs to what we're doing now as we apply it toward things that are more essential for social science than like polling or whatever. Questions about this? All right, so you can expose it to R, you can call it, you can look at a summary, and so if we think, you know, people tend to have about, you know, 30 different followers, and then there's like 10 more followers that you get because you follow 30 different people, and, you know, people tend to be sort of reciprocal and who they follow or whatever, then, you know, we get back this bivariate distribution that tends to have a mean of about 40 people following you, and you following about 40 people, of which like 10 would be overlapping or something like that. I don't know, but it can be highly skewed. So the maximum value of these things can be, you know, much bigger. But if we were going to be estimating a model on actual Twitter data, then we would want to allow these lambda parameters to vary as a function of covariates. And so rather than having like one lambda for the whole Twitter verse, we would want to say, well, what makes some people have more followers than others, which is kind of what we were getting at on the third problem. If we wanted to, you know, do something like this in Stan, we would need to specify the posterior kernel and then condition on the observed count data in order to update our beliefs about the lambdas. And so I gave you the log factorial function, which just calls log gamma. I messed up slightly with the signature of the bipoisson kernel. I didn't put rate 1, rate 2, rate 3, so I had to clarify that on Canvas Wire, but hopefully you saw that shortly after I put it up. Anyway, so, you know, pull out n, which is the number of observations that you have, and then first calculate the contribution of the prior to the log kernel. So those are going to be exponential LPDF for log PDF for lambda 1, lambda 2, lambda 3, which are really the main arguments to a kernel function. So that is going to be the contribution for the prior. And then we're going to want to make one contribution for each of our n observations on the two variables that we're modeling. In order to do that efficiently, we can calculate various constants in advance that don't vary by n in this case, although in a more complicated model they could. So the sum of the lambdas, the log of lambda 1, lambda 2, and then the log of lambda 3 minus those in order to get that ratio term that's under the summation on Wikipedia. Then we loop over the observations to get a contribution for each observation to the log likelihood function. We pull out x1 and x2 out of this n by 2 integer array that we have. We see which one is the minimum of those two values, and then we set up a holder vector of size k plus 1 to hold the contributions in that summation that was in the PMF on Wikipedia. And so we want to put into each of those the logarithm of the term inside the summation, which is going to be just some L choose and another L factorial, and then k times this log ratio. So that gets us the term k equal 1, k equal 2, all the way up to capital K. And then we can stick in the k+1 position the contribution when little k is 0, which in log unit is also going to be 0. And then we can do, out plus equal, the sum of the lambda pieces, which is the first thing, and then there's exponent times logarithm of the base minus factorial of the observations. We have that for x1 and x2, and then log sum x applied to the holder of the logarithms of the terms under the summation. And so log sum x is going to x or anti-log up each of those log contributions, sum them, take the logarithm of the sum, but it's going to do it in a way that's numerically stable and isn't going to overflow, which otherwise you would definitely run the risk of that happening if you were to apply this to real Twitter data, because like the biggest number you can take the factorial of on a computer like that is 170, and there's certainly people that have way more than 170 followers. So you need to keep all your calculations in terms of log units in order to handle stuff like that without numerically overflowing. And log sum x is one of these core tools that allows us to do that when our likelihoods or our priors have summation from this to that, sometimes an infinite summation. And so we want to be using those whenever we can, these more numerically stable operations. Questions? Nope. Okay. So when we actually apply this to Twitter, since RCNRM doesn't have the bivariate Poisson, we just do a Poisson of the number of followers of these accounts that got indicted like last year or something as part of the efforts of the Russian government to destabilize the election leading up between Hillary Clinton and Donald Trump. So we get the data on those accounts, we load that in, and then we can make some additional variables. Different people did different things. One thing you can look at is the time zone on their Twitter account from the United States or like Moscow or whatever. So apparently some people were logging into like US VPN servers and then connecting to Twitter to make it look like their account was for someone in the United States. Others were just like lazy and just logged in from like Russia somewhere. Sometimes people had like descriptions of themselves in their Twitter profile that were in Russian. So how it is anyone got fooled by that is a little bit disturbing. Anyway, you can check whether their description of themselves was in ASCII, which is sort of a bare minimum to suggest that they might actually be an American, but that may catch some other people in other languages, but also ASCII. Then we can get some characteristics of the tweets, like how often do they mention Clinton or Trump or someone's lives matter? How often are they replying to somebody else's tweet? Is the tweet in ASCII? How many hashtags does it have? Does it have URLs? Things like that. So we can create those variables and then use dplyr to sort of calculate up the average number of tweets people have that have this or that characteristic, and then merge it back into the user's data by user ID to get some additional predictors that we can use. So we're ready to estimate a model now. What a lot of people on Campus Wire were doing, we're using some other variables like the number of favorites in the account, like the number of likes or something like that, all of which are more plausibly consequences of the number of followers than something that could be plausibly an exogenous known in a model, a generative model for how many followers you have. And when you start just throwing in variables willy-nilly, including things that are a consequence of your treatment variable of interest or a consequence of the outcomes, that doesn't make sense as part of a generative model. It doesn't make sense to say, you know, the number of friends or whatever you have is just on Twitter is a exogenous known that just kind of falls from the sky, and then that determines how many followers you have. So, you know, some stuff about the nature of the tweets that you're putting out there, or you know, the time zone or the language or things like that. But anything that's sort of a consequence or correlated with a consequence of the number of followers or the number of people you're following doesn't really make sense as part of a generative model, and it makes it impossible to interpret any of these coefficients in like a directed acyclic graph if you're conditioning on something that's downstream of the outcome. Anyway, so I estimated this one, family equal Poisson, QR equal true, just using the default weakly informative. Normal priors, totally fine for a problem like this where we honestly are, you know, pretty uncertain about whether any of these things make a difference, but they actually kind of do, a lot of them. So, you know, if you were, you know, some of these things have negative coefficients, which is a little bit surprising, particularly for the Clinton variable. So what proportion of the time do the tweets by that account mention one of the Clintons, presumably Hillary Clinton mostly. But, you know, if this was sort of a propaganda effort by the Russian government, they might be a little bit disappointed that the more these troll accounts are tweeting about Hillary Clinton, you know, you would expect them to have less followers. But yeah, so certainly tweeting in ASCII tends to mean you have more followers, I guess, particularly from Americans if you're replying to other people, you know, stuff like that. So in terms of bounding these away from 0 with like 90% intervals, in this case, all of them are. But some people were using like the number of status updates that you have on Twitter, and that coefficient was like so small that it was basically, you know, consistent with 0. You could get the same conclusion by doing a plot. In order to see it on a reasonable scale, you need to like exclude the intercept and some stuff like that with a regular expression. But all of these are estimated such that the 90% credible interval is less than the width of the dot. So either on the positive side or the negative side of 0. And then in terms of visualizing, you know, one of those things. So if we want to do like the Clinton variable, let's say, we can make a copy of our data frame that was used when doing this with model.frame. That already takes into account that some observations have to get dropped because they have missing values on whatever. And then just like set all of those to 0, which is to say, imagine an account that never tweets about Clinton. What would it have is its posterior expectation for the number of followers, and then change that to be 1, which is to say all of their tweets are about Clinton, and find out what the prediction of the conditional mean would be in that case. Take a difference, or in this case, I take a difference and divide by the baseline in order to put this in, you know, relative terms. And here's a histogram of the posterior distribution on that, and that would suggest that, you know, if you had 2 otherwise identical accounts, the one that's always tweeting about Clinton would have like reduced by 2/3 the number of followers for an account where there's never any tweets about Clinton. So that seems a bit unusual given sort of the nature of what these accounts were up to, but update your beliefs. Questions? All right. So today we want to talk more, we've talked about it a little bit so far, but not in very much detail, about model diagnostics that you can do to assess whether your priors are reasonable, whether the posterior distribution is reasonable. And so for doing that, whether it's reasonable or not, we have to say that as an employee of Columbia University, as a sort of stand, which Columbia is trying to get grants to continue to develop, that creates the appearance of conflict of interest that you should be aware about before learning how to tell when something has gone wrong with the posterior distribution that you estimated by Stan. As an example, I want to use like a not very good model on this data set about political economy risk in like the 1990s of different countries, and in particular, modeling the logarithm of what's known as the black market premium. So the ratio of the exchange rate you can get in that country for dollars like on the street divided by the exchange rate that's offered by actual like banks and stuff that are certified by the government. And so in a number of countries, it's often the case that the exchange rate that they will give you for local currency to change it into dollars is less favorable than what the actual purchasing power of a dollar, would be in that country. And so you get this ratio of like the actual price of a dollar to the official price of the dollar. Take the logarithm. That's what's known as the logarithm of black market premium. It is sort of the indication of how the country is intervening in the exchange rate and whatnot. So I'm just going to blithely predict based on all the predictors in the thing except the country name, which is just a string. I do have a pretty low R squared as to how much of this we can explain. I used an adapt delta that's a little bit too low, and it resulted in one divergent transition, just so everyone would have a chance to see what that warning message looks like. If I made this a little bit higher, that would easily go away. There's other problems with the model, but I just sort of intentionally inflicted that one upon myself. So first thing we want to talk about is our package called ShinyStan. So for models estimated by RStan arm, and later we'll learn VRMS and some STAN models, it's fairly easy to investigate a whole bunch of things using the launch ShinyStan function, and we're going to see that in a second to sort of interactively click through a bunch of plots, almost all of which can also be generated programmatically, like in our markdown file. It doesn't require clicking, so you should do those. For models that you write yourself in the STAN language, you can do ShinyStan, but it is enhanced. For models that are estimated by RStan arm and VRMS, it has some additional features because it knows what the model is, whereas if you write your own STAN program, R doesn't know what that model was about, so it can't do as much with like posterior predictive diagnostics and things of that nature. Anyway, to do this on your own laptops, you can just do launch_ShinyStan for an object produced by one of the fitting functions in RStan arm, and it will look. But why am I waiting? Yeah. Okay. I guess I got tapped out of the RStudio Cloud server, and so that's going to take a second for it to log itself back in. Come on. All right. So resuming session. All right. So I estimated that model already, and I'm going to call launch ShinyStan on the posterior object for this political economy risk thing. It takes a second to pop this thing up in a new tab in your web browser, which I need to make big again. Bigger. Okay. Then you're ready to start clicking through stuff. So we can start with diagnose. So I should say this ShinyStan, our package, was written almost entirely by Jonah Gabry, who was in the QMSS a few years ago, and this was basically, or the outgrowth of this was basically his QMSS thesis, but it is really good. So you can see, trace plots, which, if you saw the video of Dan Simpson, he said were useless, and, they kind of are, but a lot of people who are sort of coming from bugs like to see those because that's about the only diagnostic you can do with bugs. What's more relevant in STAN is if you click on the thing for divergence information, it'll tell you some stuff about that. This one only had one divergence, so these plots aren't too useful. But if there were more divergences, you would maybe be able to tell something about the pattern as to what part of the parameter space they tend to occur in. Tree depth, it tended to pop out at 7. Like I said, that has a default of 15. If you'd hit the limit, you would have gotten a warning message about that already, saying to increase it. But one of the good things about ShinyStan is that if you forget the definition of one of these things, you can click on help and it'll have either a definition and or a link to more information about what each of these things are. We can also see numerical version of the same stuff. Actually, I think this time I didn't actually have any divergent transition. It depends on the seed. But anyway, it was not super great. The ratio of the effective sample size to the nominal sample size, like I said, sometimes that can be above 1, but in this case, it's mostly about 1, except for one parameter, which is a little bit less. Anyway, that's all fine. But you can see that here, in addition to like the R hat statistics, which if they're noticeably far away from 1, which suggests your chains had not converged to the same distribution, which is bad, but that's almost always going to be fine with R-stan arm. Here we can see, autocorrelation plots. It dies off quickly. That's why you get this really good effective sample size. And probably the most useful thing is the PB check for posterior predictive check. So it's going to be drawing from the posterior predictive distribution of your model and comparing it to functions of the actual outcome. So this is a histogram. So in the dark blue here, we see histogram of the actual data on the logarithm of the black market premium in various countries in like the 1990s. And then here we see 8 sets of realizations from the posterior predictive distribution as to what it thinks under the model the marginal distribution of the outcome should look like. And you can already see that, one, it's not real consistent, but it's never that close to what the actual data look like. And that already suggests there's something not good about your model, or in this case, many things that are not good. I can click on the button for overlay densities. And so now I have in my dark blue line a density plot of the actual just observed data on logarithm of black market premium. And I don't know if you can see that so well on this screen, but there's like a whole bunch of thin gray lines that are not as distinct as the dark blue line here. Anyway, those are all the density plots from like 25 realizations from the posterior predictive distribution. And if this were a good model, you would expect to see the density of the actual observations being, resembling the density of the posterior predictive distribution across observations. And in this case, there's some, noticeable discrepancies. So the actual data has this like second mode over here that is pretty much being like completely missed by the posterior predictive distribution under the model. So that would be suggesting you're omitting some variable that causes countries to like go into two groups. And the most prominent variable probably is like, does it have a floating or a fixed exchange rate, which was actually not one of the predictors, but it would be like the most obvious predictor to put in to a situation like this. So, you know, more bad news. This thing, distribution of test statistics, is maybe not the best choice of words because it has pretty much nothing to do with what people usually think is the distribution of test statistics in like a frequented sense for testing a null hypothesis that some coefficient is 0. So it should have just been distribution of statistics because, you know, for any statistic t that you can calculate about your outcome, you can calculate it on a predicted outcome under your model and see if those are in harmony or not. In this case, the mean of the actual distribution is pretty close to the mean across realizations from the prior predictive distribution, posterior predictive distribution. But in a linear model, that's a really low hurdle to get over because your model has like an intercept in it and it's like modeling the conditional mean. So you can get that sort of right on average, even in models that are terrible. It's better to look at some statistic that does not sort of map on one-to-one with your model, like the standard deviation that is like also doesn't look so bad in this particular case. But if you start looking at the minimum of the data and comparing that to the minimum realization across posterior predictive distributions or the maximum, now you start to see, you know, some funny business going on here that the actual minimum in the data is considerably larger than the minimum in the posterior predictive distribution. And so that is again suggesting your model is not handling the lower tail of the outcome very well. You can do scatter plots for the average of the posterior predictions versus the actual values. And yeah, certainly you've got a lot of spread at the top end, but also a lot of clumps of points at the low end that your line is just not intersecting through. You can make residuals, which are actually probably should be called errors, but in any event, the difference between the observed outcome and the posterior predicted outcome, the difference of those two things is the errors, and you can get a distribution of errors for any observation because you have multiple realizations from the prior posterior predictive distribution that you can subtract from the observed outcome to get those residuals. Here, yeah, does not really look normal, which is one of the things that your model would be assuming. But anyway, you can get more information on those things from that sort of tab. Questions about any of those? So this is some of the things that were talked about in the paper that was on the reading and the video in terms of sort of interrogating your model to see if it makes sense. And in this case, there's plenty of stuff to call that into question. Not so much because Nuts did a bad job, but just because the model doesn't fit that way. So that's in Diagnose. We can click over to Estimate, and we can see the plots. You see some of these plots before as to what you can get at. It only displays like 10 parameters at a time, but you can add additional ones. If it didn't show the ones that you wanted, you can type in those. And so this is the coefficient on per capita GDP. So it sort of has a 90% interval that overlaps with 0, but there's some tendency for countries with higher levels of per capita income to have less black market premium. You can get this version of the posterior summary in here, and so that also enables searching by regular expression if you have like something with like way too many parameters that could be looked at in one table. If you need to generate LaTeX to put it in a journal or something like that, you can click on this thing and then click on that. It will spit out the code. Really should not be that computationally. Okay, it was just frozen for a second. Anyway, if you need to put a table into a publication, this can generate a correctly formatted version of that. So that's nice. Clicking on the Explore tab enables us to look at some more of these plots. What I particularly like are the bivariate. So here, can we get the correlation or the bivariate distribution between like the R-squared variable and like the coefficient on GDP. So not a whole lot going on in this particular case, but we can see realizations from the bivariate distribution of these things. We can even see the trivariate distribution. So this is going to be some WebGL business. You can make it bigger, or you can, how do you submit in and out? Anyway, you can turn this thing around to get like a better look at all. But in this case, it's just kind of a blob. But at least you know it's a blob. So yeah, and then you can get density plots. You can get histograms of whatever parameter you want just by clicking through all this stuff. Any of these plots you can download as a ggplot2 object, load it up in your own R session, and like change the theme to whatever your like personal ggplot2 theme is. Or if you just like want a PDF of this thing to stick in something else so they don't have to look at it in a web server, you can click on the PDF thing and it'll download you a PDF of this plot. So you click on more, there's a glossary, which is good, of these terms, where you can get more information in terms of help for how to use these things. Yeah, it's mostly Jonah, really entirely Jonah pretty much. But there's another person who's starting to work on it now. There's a notepad where you can write yourself notes about a model in case you want to remember it. Also, it's not great in this case, but if you want to look at the underlying Stan code, you can. In this case, it's not really that intended to be read by a person, particularly people who are just sort of starting out with Stan. So I don't think this would be that helpful at this point, but when you start learning more about how to do things in the Stan language, if you see a ShinyStan of some other model, or you forget what your model was, you can click in this thing and see the code that did it. But yeah, I had to define a kernel function for this linear model like that. So that is, I guess, about all you can do with ShinyStan at the moment, but that is like a lot of stuff that I went through kind of quickly. So any questions about those sorts of things? I'd say probably the most important thing to focus on, presuming you're not getting a whole bunch of warnings saying like divergent transitions and like hit the maximum tree depth and all that, which is pretty rare with our Stan arm, would be to look at these posterior predictive checks to see, okay, is your model making sense? Is it compatible with the data that you modeled? Is it consistent with the assumptions that you made? Those sorts of things. Questions? Okay, so then you can click close, and you're back to your RStudio session, and we're back to the slides for today. Right? So those are all the things that you can do with ShinyStan. In the bayesplot package, which is also written by Jonah, a lot of these plots and some additional ones can be generated statically. So if you just invoke the available PPC function, that will tell you all of the plots that Stan or bayesplot is capable of doing pertaining to posterior predictive checks. So these ones for like bars and stuff, those only pertain to outcomes that are discrete, whereas this outcome was continuous, but we have different ways of visualizing the posterior predictive distribution when the outcome is discrete versus when it is continuous. So we'll look at some of the continuous ones today. Again, going through these pretty quickly because kind of once you've seen one, it's fairly easy to figure out how to make the rest of them. And there's a function in RStanArm, or it's a method in RStanArm called pp_check for posterior predictive check, where you give it the result of your function that was fit in RStanArm, and then you say what plot function you want to do. So basically, you just take one of these things and remove the leading ppc_, just leave the rest of it. That tells you what to put for plot fun, that string, and it'll make a plot like that. So this is this overlaid density plot that we saw before in ShinyStan, again showing the actual data has the second mode in the marginal distribution of the outcome that's not being well captured by our model, presumably due to omitted variables. The thing that comes out of ppcheck is a ggplot2 object. So you can do plus and then say stuff about the legend or the color or the theme or the axes and stuff like that. So here I move the legend, dark blue means data, light blue means predictions, to the bottom of the plot. But anyway, a lot of these things are just calling pp_check with different options for the plot fun. So another one of the things that we can do, this is similar to what we were doing last time, but maybe a little bit better. So we can make these like 50% posterior predictive intervals, and we would hope to find that about half of the observations fall within 50% central interval, 25% fall below, 25% fall above. This ppc_intervals_group function allows you to specify a grouping variable, such as does the country have an independent court system, which is another thing that is sort of associated with not having as much corruption in like the exchange rate markets and stuff like that. So this is for countries that have like kangaroo courts, and this is for countries that have like reasonably independent courts. And you can see that looks like one of the problems is there's a bunch of countries with like independent courts that have like the lowest possible value of black market premium that isn't being captured so well, and as a consequence, it doesn't feel that great with the upper tail either. But overall, if you calculate the numerical, what proportion of times does this fall in the 50% interval, comes out to be about 0.6, so overfitting a bit more than what we were doing with the diamonds model. But remember, you can overfit part of the data, underfit another part of the data, all simultaneously. So that's oftentimes more evident in the plots than it is from these aggregate numerical summaries. But in any event, this one has a tendency to overfit, even though it fits badly. So it's certainly not doing well at like the lower tail and stuff like that. Unlikely to predict future data from these same countries well in like subsequent years. This was in the 1990s or whatever. But oftentimes when you do the lazy thing, just like put all the predictors you have into the model without doing any thinking about where the interaction should be or anything like that, you will often get a model that doesn't fit well, but it's evident that it doesn't fit well if you bother to look. So Stan is extremely good at drawing from posterior distributions. And it's basically gotten to the point where it'll either do it well, or you're going to get warnings that say, this did not go well. Not a whole lot in between. But, you know, that's about all Stan. It has a little bit more going for it, but it's basically just good at estimating, drawing from posterior distributions that are well specified. But it's up to you to come up with good models for these phenomena that are of interest to you. And think about the generative process. Think about where the nonlinearities come from, all those sorts of things, rather than just say, like, throw everything you have into a logic model and, you know, make predictions. But if you do that, you should at least see when and where your model is not doing good, you know, such as like over here and up there. And that should spur your thinking as to what you could do to create a better model for an outcome like this. So, like we said, there's a little bit of a problem with posterior predictive intervals being conditioned, or from a posterior distribution that conditions on those same data. So one thing you can do is obtain leave one out predictions. So what if we left off the 20th observation, reweighted the posterior distribution, predicted the 20th observation, compared it to the actual value of the 20th observation? So we would get like this distribution here for the leave one out predictive distribution, and the actual value was this, something outside the 50% interval, but well inside the 90% interval. So these are a little bit better for making an assessment as to how well this model would predict future data. And you can see, particularly in the tails, not doing so good. So models that overfit the past data tend to underfit, fit poorly, predict poorly future data, even if it does come from the same data generating process. And that can be accomplished using plot fun equal Lu underscore intervals to obtain that. Another leave one out based method is Lu underscore pit underscore QQ. So pit stands for probability integral transform, which is basic, and QQ stands for quantile plot. So this is basically looking at the inverse CDF of the data and comparing it to inverse CDF transformation from the leave one out predictions. If a model is good, all of the points should line up on the 45-degree line. This is not so great, even though from this plot it doesn't seem as horrible as what it actually is. But sometimes this plot is really good for telling you, you know, when you have problems, it's sort of tail in the middle or whatever it might be. So this over here is sort of another way of seeing that the actual data have this second mode that is not being captured so well by the model. Rolling along, you can do plot fun equals scatter, 3 realizations from the posterior predictive distribution, scatter plotted against the same actual y values, and it's clear that even when the model is like sort of predicting in the right center, there's a whole lot of noise around that line, and then at the bottom there's points that are just not well handled by a line at all. So that can be good for you know, detecting some forms of nonlinearity. But a lot of these plots are sort of similar to some of the diagnostic plots that you probably should have learned when you were first taking like a regression-based class, like comparing y versus y hat. But in this case, the y hat includes noise because we've estimated the standard deviation of the errors. But a lot of it is similar concepts. It works better because we actually have a distribution of conditional means, a distribution of errors, a distribution of anything we want. So we can say, you know, is this misfit, you within the realm of probability or not. Here's another thing, and it's similar to the histograms plot with freak poly, that can, in this case, there's so few data points that it looks a little weird in my opinion, but when you have a lot of data points, sometimes these polygon frequency things look better than the histograms. In any event, this is the one for the actual data. Here's 8 realizations from the posterior predictive distribution, and none of the 8 realizations look that much like the actual data, which is old news at this point. We can group those things by the Quartz variable or whatever we want. We can overlay, some sort of statistic. Here is the sample median, which looks reasonably well for places that don't have real court system, and not as good for the countries that do have independent judiciary branch. Another thing you can do is plot fund equal ECDF overlay for the empirical cumulative distribution function. So the one in blue, again, is for the actual data. We have a whole bunch of gray lines, each one representing a realization from the posterior predictive distribution. And again, you can see in the lower tail here, the model's empirical CDF distribution is not that well aligned with the empirical CDF of the data, suggesting an omitted variable that is common to countries that have low black market premium. There's also a bunch of plots that are available in CMC. You can see the names of for sort of assessing the performance of the MCMC algorithm, even though for STAN, and particularly RSTAN-ARM, tends to work well. So here's autocorrelation plots. You can see the first order autocorrelation of some of these things is negative. That's what enables STAN to be super efficient. These ridge plots are like very popular these days. Another way of assessing how concentrated the posterior distribution is, which is not at all for most of these variables, but for like GDP, it's a little bit better, and R squared obviously is bounded between 0 and 1. You can see some stuff about the posterior concentration. A lot of these functions allow you to specify pars, which is what parameters you want to plot, or regex pars, which takes a regular expression. Here I excluded the intercept because it just threw off the scale of everything, but I had to use a regular expression in order to do that most efficiently, just excluding anything that starts with the open parentheses. These ggplots in 2 dimensions are known as hexagrams, so they're really just squares that are filled in different colors to indicate more density in bivariate margins of a posterior distribution. Better, in my opinion, is the pairs plot. This is in RSTAN-ARM and in STAN, where you can look at a bunch of bivariate margins simultaneously. And finally, the parallel coordinates plot, which didn't actually help that much in this case because I didn't have any divergent transitions to speak of. But you saw a plot like this in the reading when there was more divergent transitions, and you can sort of trace it to what variable is it extreme on when most of the divergent transitions start. That can give you some indication as to what parameter you need to maybe reparameterize in order to overcome this divergent transition problem. But we'll see more of those when we run into models that don't work as good. Okay, out of time for today. Pick it up next week with more stuff that you can do with draws from a posterior distribution once you have it. So, see you then.